this video, we are going to see how you can design a microstrip patch antenna for a particular frequency and how you can simulate that in CST. So in this video, we are going to simulate an antenna for 2.4 GHz on a substrate of FR4 having thickness of 1.6 mm. So to design an antenna, these are the main design steps. So initially we have to calculate the width of the patch, then effective dielectric constant, then extension of the length and actual length. And usually in microstrip patch antenna, one of the feeding technique is inset feed. So in this simulation, we are going to see how you can uh, design these type of inset fed antennas. So calculate the position where the input impedance become 50 ohm. That is the final step, and then simulation and optimization. So first design step is we have to verify the dielectric that we are going to use. So our resonance frequency requirement is 2.4 GHz and the free space wavelength corresponding to that can be calculated by the equation C by F. So that will give you the wavelength 125 mm. So our condition for the dielectric is the permittivity has to be within the range from 2.2 to 12. So in our considered material, the permittivity is 4.3, which comes in between, and the thickness has to be within the range 0.003 lambda 0 to 0.05 lambda 0. So if you substitute these free space wavelength, you can see that the thickness of the substrate 1.6 mm comes in between 0.375 to 6.25 mm. So the selection of the dielectric material is okay. So our first thing is we have to calculate the width of the patch antenna. So width is given by the expression C by 2 FR in the square root of 2 by epsilon r plus 1. So FR is the resonant frequency, epsilon r is the permittivity. So here in our case, 4.3 is the permittivity of the FR4 that is considered here. So based on that, by substituting these values, we can calculate the width. So it can be given by this value 38.38 mm. Sorry, this is not meter. So I have converted the value get in m to millimeter. So this is the value in millimeter. So this is the value in meter and this is the value in millimeter. And next is calculating the effective dielectric constant. So the effective dielectric constant can be calculated using this expression. So here we have to consider the calculated width and height of the dielectric constant. So if you substitute these values, you will get the value, because here we are considering all the parameters in millimeter, 1.6 mm, 38.38 mm, which is the calculated value. So we will obtain the effective permittivity as 3.997. So our next step is to calculate the patch length. So these are the steps for calculating the patch length. So in our video on the rectangular patch antenna, we have seen that there will be fringing effect, and because of the fringing effect, the effective length will be because of that fringing extension length also. So the designed length has to be L effective minus 2 delta L. So L effective can be given by this expression C by 2 FR into square root of epsilon R effective, and delta L, this is the fringing effect length, can be given by this expression. So by substituting all these values, you can get delta L as 0.7411 and L effective as 31.26 mm. So substituting L effective minus 2 delta L, you will get the length of the patch as 29.78 mm. So now we have calculated width, effective permittivity and length. If you are hesitant to do all these calculations, you can also use already available calculators like the Pasternack microstrip patch antenna calculator. So you can put the values here. So for our case, we are using the FR4 substrate having the permittivity 4.3, dielectric height is 1.6 mm. So change the dimension to mm. Our operation frequency is 2.4 gigahertz. So you can just calculate it and you will get the values here. So you can see that these values are okay. So these values, whatever we have calculated, W 38.38, length 29.78 is same as whatever we have obtained from this 38.38 and 29.7. So we can either calculate by ourselves, or you can use these readily available calculators for calculating the length and width of the patch antenna. So here you can see the calculation equations are everything from this website. So our next intention is to find this width of the microstrip line which is used to feed this patch antenna. So let's see how you can calculate the feed width. So this is the uh, calculation equation for the characteristic impedance with respect to feed width. So I have uh, taken the variable FW as the feed width dimension. So based on the feed width dimension, this is how the characteristic impedance is calculated. So there are two equations based on these parameters. If the feed width by height is less than 1, you have to use this equation to calculate the characteristic impedance, and if it is greater than 1, you have to use this equation. So in our case, our purpose is we have to find out this FW. So FW is the unknown parameter here. We know Z0 because we know the characteristic impedance required in our case is 50 ohm. So we know 50 ohm, but we have to find out the feed width. So it is always like the reverse calculation. Just put some feed width here, then calculate the characteristic impedance and make sure that it is equal to 50 ohm. So instead of doing these calculations repeatedly, what we can do is we can similarly use some already available website for this calculation. So let's see that. So for this also I am going to use Pasternack microstrip line calculator. I will put the link to this website in our description. So here you can see that this microstrip width. So here it is represented as W. So in our case it represents FW, that is width of the feed line. So height, it is the height of the dielectric. So if you have these values, you can calculate this thing. So in our case, we are using FR4 and its dielectric constant is 4.3, and you have to put everything in millimeters, and the dielectric constant, sorry, height of the dielectric is 1.6 mm. So for this case, I know that as it is FR4 with 1.6 mm, the width, feed line width is approximately 3 mm. So just we can just start with 3 mm. Otherwise, you can just put some random value and find out the impedance. So if I put 4 mm, you can see that impedance is showing 42.94. That means that you have to actually decrease this value to get to increase this impedance. So I'm going to decrease it. So here you can see that it is getting increased. So I'm going to, so now my purpose is I have to decrease this value. So that means I have to increase the width. So let's see. If I put 3.1, it is equal to 50.36. If I put 3.2, it is equal to 49.40. So it has to be in between 3.9 and 3.2. So if I put 3.15, it is 49.88. Be 3 point, oh sorry, 3.13. You can see that it is approximately 50 ohm. So width of the feed line you can use as 3.13. So this is how we are figuring out what is the width of the feed line. So we have calculated almost all the important parameters. The one thing we are missing now is this inset fade length. So we have seen in our previous video that if you know the impedance at this point, that is impedance, if you know the impedance at this point, this y0 can be calculated using this equation. So our purpose is we have to have an understanding of the impedance at the edge. So currently we don't know what is the impedance. So using CST we can find the impedance at the edge and we can find the inset fed distance also. So let's see how we can do that. Okay, let's start with new project. So I'm going to select antennas, then planar antenna. So I'm going for the time domain. As my frequency is from for 2.4 gigahertz, maybe I can put like 2 to 1 2 to 3. Okay, finish. So okay. So my first step is I'm going to design like draw the dielectric. So modeling, click on this box and click escape button. It will show the dialog box. You can put the values here. So minus d by 2 to d by 2 minus d by 2 to d by 2. So here I have taken this d is this total dimension. That is what I am going to draw now. That is this dielectric is what I'm going to draw now. That is this dimension and it has a thickness of h. It is 1.6 mm and this material is FR4. So FR4. So I'm going to select FR4. So it will ask for the dimension. So here we know that these are the dimension of the width and length. So the total dimension has to be more than that. I'm going to take it is like usually like L plus 5H. If you have that much extension along the length and width plus 5H along the width, it is okay. So now I'm going to just take 50 mm, which is more than both this length and width for the dimension of the dielectric. So I'm going to select 50 and H is 1.6. So here I have my dielectric and my next is I'm going to draw the ground plane. So similar step. Oh, sorry. Okay, so the dimension is same as whatever be the dielectric case. So you can put that value as the ground plane is coming below. You can put Zmin and Zmax as 0. You can either choose PEC or you can load from the material library like copper. So you can either use any one of this. So here I am going to use PEC. So here you can see the preview and I click OK. So now the ground is created. So I'm just going to disable the working plane so that I can have a better view. And next is now we have to draw the patch. So patch dimension is given by width as 38.38 and length as 29.78. So let's draw that. So along the x dimension, my width comes. So I am going to give minus w by 2 to w by 2 along the x, and along y I'm going to give minus l by 2 to l by 2, the length. And z minimum, that is we have to draw that on the top of the dielectric. So it is like h, and here I'm going to give some thickness to that copper. So it is, I'm going to choose 35 micrometer, that is h plus 0.035 as the patch dimension. Then click OK. So it will ask for the dimension of the W. So our designed value is 38.38 and length is 29.78. Okay, so now we have designed our patch. So now our next step is to draw the feed line. So we have seen that the width of the feed line is 3.13. So just click on this thing, and this is our feed line. So along the x, that means it is minus fw by 2 to fw by 2. So this is the width. So along this dimension it has to be like this, and y minimum to y maximum, so it has to extend from this dielectric to our inset fed position. So now we don't know at which is the inset fed position, so I'm going to put that up to this edge. So what I'm going to do is I'm going to, y minimum is from minus d by 2 to minus l by 2, and which is also from h to h plus 0.035. Okay, so it is, we have calculated it as 3.13. So you can see that it is given here. So now I have that feed line. So next, my next step is to give the excitation to this port. So what I can do is, you can zoom in, and if you click F, you can select the face. So means if you move, you can select any face you require. So my intention is to select this one, the face of the feed where we have to provide the excitation. So I just click on it, and next, our next step is to use waveguide port. So you can use here, you can see in home VBA macros, there is some port calculation. You can go to solver ports, calculate port extension coefficient. So it will show this window. So here you can see that we are going to use the microstrip line, and width is 3.13. So it is actually automatically taking that values. Epsilon r is 4.3. So you can either calculate it and create the port by yourself, or if you click on construct port from picked face, it will automatically create the waveguide port. So now the waveguide port is created. Now you have to go for the simulation. So one thing you can check is this is the mesh properties. If you want to have good accuracy, what you can do is you can increase this values, so it will give you good accuracy. Here I'm not going to increase it because as I'm using the learning edition, I have some limitation on the number of licenses. So uh, my simulation accuracy may be not that much accurate. So if you have to have the good accuracy, try to increase to 20. So if you are going to increase the mesh cells, it will means it will be having, maybe I'm not sure, will I be able to show you. So these um rectangle cells that you are seeing here is known as the mesh cells. So if you increase these things, this meshing, that is this meshing will be increasing, and the EM solution, that is the Maxwell equations solution, will be more accurate, and you will be getting more good results. So if you have good powerful computer and have the CST license, you can always increase these values to get the good accurate result. So I'm just going to use 10 10 20 val 20 here because I don't have that much more powerful laptop and I have some limitations. So click OK, and next is we have to check the background. In the background we are using the normal material, and boundaries or open space, and if you click on the open boundary you can see that these open boundaries based on lambda by 4 condition. Okay, so we have the open boundary and everything, and next you can do the simulation. So before running the simulation, I just saved the file, and this one is for the accuracy. If you set more higher values, you will be getting more accurate value. And next thing we have here is adaptive mesh refinement. If you click on it, you can select the number of passes for the adaptive mesh refinement. So if you select it, the mesh will be refined more and more, and you will be getting more accurate results. In my case, I'm not going to click on it, but in your case, you can select this thing and click on number of values. And this is the iteration delta. So you can set all these values based on your requirement. Okay, so I'm not going to set this because it will be taking more time. Okay, so next I'm just going to start the simulation. Okay, now the simulation is complete. So if you click on the S parameter, you can see the S parameter. So you can see that it is the matching is not that good, and the resonant frequency is at around 2.3 gigahertz. And so we know that now we have used the edge fed and we have to use the inset fading. So for that, we have to first identify the impedance at this point. So to calculate the impedance at this point, we can use this Z matrix. So let's see how you can identify the impedance at this point. So when you click on the port, you can see that the port is now defined at this position, and this Z matrix, that is this impedance, corresponds to this position because our port is defined at this position and our impedance will correspond to impedance at this point. But to calculate the inset, we need the impedance at this point. So what we can do is we can de-embed the port up to this point. So for that, what you can do is you can click on S parameter calculation and then use de-embed S parameter. So if you put this distance from here to here, it can be de-embedded. So for that, let's find out that distance. So I have to de-embed the port from here to here. So I'm going to see what is the distance. So this distance is around 10.11 mm. So that is around 10.1 mm. So I just delete that. So my purpose is to de-embed that. So you go to post processing S parameter calculation de-embed. So that distance is 10.11. So you have to put minus 10.1 mm and you just click apply and then OK. So if you click on the port, you can see that it is de-embedded to that point. So if you click on that impedance, you will be getting the impedance at this position. So now you can see the difference between the impedance. So if I just disable this de-embedding, maybe 0, you can see that impedance is changed. So now if there is no de-embedding, you will be getting the impedance at this point. But for my calculation purpose, that is for to calculate the inset feeding, I have to find the impedance. That's why I'm using this de-embedding. So I have to find that distance, put it there. So you can see this is the impedance at that point. That is, now you get the impedance at this position. So if you have that patch antenna, you get the impedance at this point. So So if you want to tune the resonance frequency, you can change the length parameters and tune that. Now I'm not going into that details. I'm just going to see how that inset fed can be calculated. So my resonance frequency now here is 2.3 and the impedance at 2.3 is around 70.216. So now I know the impedance at that point. So now you know impedance at this point, and using that values and using this equation, that is, you know the impedance at y equal to 0 position, and using this equation, that is y in y equal to 0 equal to cos square pi by L y0, you can calculate impedance at this position, at every positions, and you can find out at which position the impedance is 50 ohm. So you can actually find out y0. So okay, so I have a Python script to calculate this. So this is that equation, input impedance equal to RH into cos pi y0 by L square, where L is the total length of the patch, which is equal to 29.78 based on our design, and RH, which we got from the CST as 70.216. So I have given RH as 70.216, and y0 is the total dimension of the patch starting from 0 to L by 2. So that is this thing from 0, here is the 0 to up to L by 2. So I am considering up to L by 2. So I have taken up to that distances with 500 points. So if I run this script, I will get this plot which will show at which point the impedance is 50 ohm. Here you can see that the 50 ohm occurs when the offset is 5.37 mm. So this is the plot from 0 to L by 2. So you can see the offset distance. If you don't have Python, you can do the calculation in Excel also. So first I'm going to put the edge impedance, which is R0, which we got from the CST, which is equal to 70.21. So 70.21. So I'm going to use that value. And next is y0. So y0 is actually from starting from 0 to, so maybe I will start from 0 0.5, 1, 1.5, like that at an interval of 0.5. So I will use like this. So I have to only consider up to L by 2. So maybe I will just draw up to this point. And L is the total width of, length of the patch, which is 29.78. So it is 29.78 and so everything is okay. Next we have to do the calculation. Oh, sorry. So that is equal to, I have to do R in. So I'm going to do this calculation, R in Y0 cos square pi by L into Y0. So this is my calculation. Okay, what I'm going to do is, which is equal to Rn into cos pi into B2, that is Y0 divided by C2 the whole square. Okay, so this is going to be the impedance with respect to the length. So R underscore Y0. So this is R underscore Y0. So now I am going to plot Y0 and I'm going to plot Y0 and RY underscore Y0. So the plot will be like this. So this is my impedance and this is the length. So from here also you can see that the 50 ohm impedance comes at around 5.5. So this is how you can calculate the offset length. So now we know that at around 5.5 we can have that offset. So my next step is to provide this slot and extend the feed. So let's see how we can do that. So means first we have to provide a slot. So maybe I can give it as slot. So slot has to come from here to here. So we can subtract that slot from this patch and extend the feed. So maybe we can give that dimension as minus SL by 2 to SL by 2 and Y minimum. So it has to start from minus L by 2 to minus L by 2 plus Y0. Y0 is what we have calculated now, and the thickness has to be from on the top of this. Okay, so if SL is, maybe we can give it as 5 and Y0 we have seen as 5.3, right? 5.3, then click OK. So now what we have to do is we have to subtract the patch from this slot. So now we have that thing here. So to subtract, okay, okay, after subtraction you have to extend this feed to this point. So for that, what I can do is I can click on the feed and change the dimension of y. So now y is extended to minus L by 2 to y0. So it is now extended. So now we have an offset fed patch antenna. This one we can do the simulation and check the result. Okay, the simulation is complete now, so you can check the S parameter. Here you can see that the matching is getting improved when we have used the inset feed. So before using the inset feed, when it was like edge fed, the matching was like around minus 10 dB. Now you can see that it is improved and we have around more than minus 20 dB. Okay, so in Smith chart also we can see how the matching is. So if you have to see that, okay, add curve marker. If I put the curve marker here and if I enable the Smith chart, I can see where my matching is. You can see it is almost matched to 1. So only less difference. So by using the insert feed, you can see that how the impedance matching can be improved and you can have a better antenna. So this is now our antenna. Okay, now what we have to do? Okay, so now we have to see what is the electric field distribution, magnetic field distribution, and far field. So for that, we can go to the field monitor. Where is it? Field monitor. Okay, so where is the frequency? 2.32 field monitor. So 2.32. Okay, apply surface current, apply far field, apply. So I'm going to select E field, H field, and far field. Okay, maybe if you are going to use that instead of enter the calculation domain, you can select structure bounding box. So the electric field and surface current will be calculated only in this domain. So first we can do that only for the structure bounding box. Okay. Sorry, so I will delete all these things and we can define it again. So field monitor, new field monitor, E field 2.32, use subvolume structure bounding box preview. So now only this structure bounding box is selected. Apply H field also for the structure bounding box, far field also. Okay, apply. So for far field, we have to delete this and click apply. Okay. So now we have electric field, H field, and far field. We can start the simulation again. Okay. Okay, now the simulation is complete. Let's see the electric field. So as I have to see the electric field on the patch, maybe I can select the patch. Oops. Where is this thing? Okay, maybe I can use the cutting plane. So I will use the cutting plane here. So that thickness is at 1.6 mm. So this is on the patch. So this is the electric field distribution on the patch. So by just dragging, you can change the by just dragging you can change the distribution in a more visible manner. So if you go here, you can select in which pattern, in which order you have to see, like contour, arrows, or uh, iso lines. So I'm going to use the contour. So if I use the animation field, it will be very easy to understand. So this I'm going to use like this. So if I use the animation, you can see that the electric field is more on the edges and uh, electric field is minimum at the centers. Okay, so now we can, in a similar way, we can see the surface current. So if you increase the surface current, okay, maybe I can go for arrows. By using the arrows, you can see that the current distribution is more at the midpoint and minimum at the ends. This is what we have seen on the explanation on the rectangular patches. As these are the open slots, current will be minimum at the edges and the current will be maximum at the center. So you can see the arrow changing with respect to the wave propagation. So if you observe the far field, you can see the far field distribution and show structure transparency. Maybe I will make the far field transparent, and this one can be used to reduce the size of the field. So here you can see that almost all of the field is extended in this direction. That is, it has a broadside pattern. There is negligible radiation below the ground plane. So this is how the pattern of the patch antenna will look like, and all the radiation is mainly concentrated above the patch. Okay, so maybe we can see the fringing field again. Okay, oh sorry. So cutting plane is at 1.6. So if you zoom here, maybe we can to see the fringing field, because the fringing occurs along this point. So you can cut along the length to see the fringing field. So we can see that the fringing field is occurring at this position. So maybe I will cut along this one, that is x-axis. I'm going to cut, and oh sorry, x-axis I'm going to cut. Maybe I will remove this bounding box for a better view of the fringing field. So here you can see that the fringing of the field happening here. So now it is on the feed line. I may have to move a little bit. Maybe we can move to 5. So here you can see that the fringing field happening on both the sides. So maybe I will stop animation. Okay, so the animation was good. Okay, so I'm just changing these values to show the fringing field. So here you can see that the change in arrow direction here, when the arrow direction is going up, this will be going down. So here you can see the half wave distribution and the arrow direction of the fringing field. So maybe I will stop it here. So here you can see the arrow direction easily. So this is what we have seen in our PPTs. So in our PPT we have seen that how the fringing field will be. So you can see that at this end it will be coming towards, and at this end it will be going towards, and it will repeat like this. So this is what we are seeing now on this thing. So the fringing field coming from the ground and which is extending through the air. This is what we are seeing now on this animation. So I hope you get some idea about the simulation. Hope all this video is helpful. Thank you.